Hi everyone, this is a video presentation of my solution for 2016 Putnam competition problem B2. So here's a statement of the problem. So I want you to spend a few minutes and read about the problems and especially pay attention to this underlined part. So I hope you managed to understand the meaning of a number being squarish. And here they're asking actually twofold question. If this quantity, the limit behavior of this quantity exists, compute it and decide whether it exists or not. If not, and prove that no such constant exists. And let me share our answer first. We find it actually exists, and we're going to introduce this alpha and beta. Before we do that, this is a typical question in number theory. If alpha here, that number we're pointing, if this is 1, this is usual average number of a squarish integer up to n. But sometimes the number of them compared to n is very small. Sometimes we have to look at this right portion, so that measures the magnitude of this n, how fast this Sn is growing. So if alpha is not 1, or if it is less than 1, often the average number of things in between 1 and n turns out to be 0. So we need more information than that. So we consider something like this. Different function than n to the first, some right function to put in here, so can we measure actual number of squarish integer between 1 and n. It's represented compared nicely to n to the alpha. Sometimes we have to use a different kind of function than this power of n. But here they're claiming that if it's asking if it's possible to write it in terms of n to the alpha. So here we're analyzing the problem in slightly different perspective. Rather than fix n and counting how many squarish numbers are there, we actually look at this number square and see how many squarish integers are around that given number k squared. So a squarish number that is to the left of a perfect square k squared, is ak, and to the right side is a bk. So this is next perfect square to the left and right. So I guess we're going to look at in half in here. So the squarish integer that's to the right of k squared is closer to the k squared to the left, and if this being a squarish integers, that should be closer to the k squared than k minus 1 squared. So for given k squared, we're going to count how many squarish integers are there to the left and to the right. Yes, I was wrong about my notation ak and bk. This is not squarish integers, that's the boundary where it's closer to that k squared, and here close to that k squared in there. So that's right in the middle. So to the left is k minus 1 squared plus k squared. Those are the 2 points. Right in the middle would be this half angle midpoint formula. And to the right, bk, which is to the right is a k plus 1 squared, to the left is a k squared. So applying midpoint formula, we get to the left. Fortunately, this turns out to be always half integer, not being an actually integer, so you can decide how many integers are close to that. So this exact midpoint is never an integer, so there won't be any integer that has the same distance to the left and right. So we have a definite answer for number of integers that are close to the k squared to the left and right. The same thing in here. bk, this exact midpoint formula happened to be a half integer not being actual integer, so we can see for example, the smallest integer a largest integer that is closer to k squared in there. Then we call this interval from ak to bk qk. So I guess our goal is that given k squared, between ak and bk, how many integers Squarish integers. So if you subtract this, compute the distance from to the k squared, that itself being a square again. So let's translate that to algebraic term. If x is a squarish number in qk, so that is compared always with this k squared, that means x minus k squared is either positive j squared or negative j squared. The difference must be a perfect square. So if we rearrange it, x is always in the form of this parameter part k squared plus minus another perfect square. Right, I wrote down formula of AK and formula of BK there. And we're counting how many squarish numbers are to the right side of k squared. At this point, we're not including k squared, but we'll definitely include that when you're counting a squarish number to the left of k squared. So if there's ever a squarish number to the right, that should be in that form, and that should be less than or equal to this bk. So the j is varying from 0, not here to 0 because it's greater than, it's 1, to some number, such that these two things, this inequality holds. So if you solve this inequality for j, and then we have, because it's to the right, I think we have to choose a positive there, because it's to the right side. So j must be in between these two. So j is the, starting from 1, go all to the largest integer, and that is less than the square root of k. Right, to handle this number of squarish integer to the right nicely, I introduced this quantity epsilon k. So this is usually irrational number. So if you subtract a small amount, absolutely less than 1, so you can make this, turn this number in the upper bound to actual integer. So rk is an integer by subtracting small amount of quantity between 0 and 1. K can be perfect square itself, so sometimes this epsilon k is a 0. So by subtracting a small amount, we turn this right bound to integer, which I call rk, r representing the right side. Right, here we are counting the left side. Like I said before, we are now including k squared as a possibility, and calculate k squared minus j squared, and that's to the left side. And this is ak. And I think this is a mistake. I don't see why I didn't include that equal symbol there. There should be less than or equal to, and this is just one count. I don't think it's gonna create a whole lot of problem to my solution, so I hope this is gonna go okay. Alright, now if you solve for j for that part in here, j is going to be greater than or equal to 0. And if you deal with this side of the inequality, then you get that. Like we did it before, we're going to subtract delta k. However, I didn't subtract it from square root of k minus 1. I subtract from square root of k. The reason is that so that I can compare the count in the left side and the count in the right side, kind of play with the same magnitude, root k and root k there, so I don't have to deal with square root of k minus 1. And let's see if I can justify this strictly less than, not equal to. So the case where the delta k is allowed to be 0, that will be k being a perfect square to turn this one as into an integer. If it is a perfect square, except 1, this is unlikely. This is going to be a perfect square, so you have to push it further down. And if not, you have to subtract a little bit, get down a little bit further down to this level. So I claim that this greater than part of delta k is justified. You actually have to subtract positive quantity to count this correctly there. Rather, I'm using delta k again to compare it. When you combine these two things together, it's a little bit simpler formula. Then the count in the left-hand side would be this number plus 1 because we're counting 0 there. Just realized, unfortunately, I did put this less than equal that I missed here. So that corresponds to the correct, I got this correct inequality there, which I forgot to put the correct inequality there. Alright, so this result is correct. The mistake I got from there, it's really a typo. I did it correctly here. Now altogether is the number of squarish integers around k squared. Is that from the left side and right side altogether we have this many and we have that many. So we have 2 times square root of k, there's 1, and there's a small terms epsilon k and delta k that are involved. I looked at the next slide, but I want to refer back to this portion here, and this is a small quantity, so what we care about this quantity is the size, how much it varies. So if you add this epsilon k and delta k there, you can see epsilon k there and delta k there, it is less than 3 and absolutely greater than 0. That's how much it is varying. So if you go to the next page, as you can see, we have this pk is summarized there, and this sum of these two error terms, I call it mu k, is varying 0 to 3. So with this much of a setup, let me claim that counting the squarish number all the way up to not just random n, but a perfect square, square of m, then it is right bound, so we can count it with this setup. We can count it easily. So here's a situation that's the first integer m at 1. The last number we're going to look at is not random n, but perfect square m squared, as you can see in there. So how many squarish numbers are there? If you look around 1, and 2 squared, and so on, up to all the way up to m squared. So we're going to add up all the squarish number we have in there, and this formula holds nicely around 1, which I checked. I might have it stated in the next part, but if you look at the last part, we only count all the way up to the left side of a squarish numbers and the left side of m squared, and we're not counting right side squarish number, which you have to subtract off. Then the right side of a squarish number, it is subtract off after you add all these pk's, which include this right side squarish number. In the definition, in the right side of squarish number, we did not include m squared wisely, so that this is the correct thing to subtract. We don't have to worry about whether to throw back in m squared or not. This rm does not include left bound in there. Alright, so if you do that and look at this part in here, so think about replacing pk, which is count around the k squared, with this one and go through all the sigma 1 through m. Of course, 1 becomes m, it's a constant, and there's m times. We have this one showed up exactly like that, 2 times the sigma root k, and these are separated like this, and we can estimate this number, and rm is this one and plus epsilon m because it's negative. So that's number of squarish numbers up to m squared. Right, here's the thinking. We know what this one is. We know kind of upper bound of this one, even though it's very difficult to exactly calculate this guy. This is very small, a little increase. The major part that increased fast is this one, and this is also predictable. So we're looking at this expression and give this thinking. If you, well, the whole idea is a Riemann sum. We can turn this term in here into a Riemann sum, right? In the Riemann sum, you see something like that. So Riemann sum involves k divided by number of partition there. So I inserted m there. Not inserted, I'm just comparing this one with Riemann sum. So if you think about this type of Riemann sum that approaches this definite integral, and this is a delta xk. This part's a delta x, and that's the function part. This is xk, right end of the kth interval, things like that. So if you look at the Riemann sum version of this definite integral in here, you will find this one, this expression. So because m is relative constant for this sigma parameter, and you can pull this outside, and you can see the motivation from this one. This is 1/2 power. There's a full 1 power. So altogether, this 3/2 as exponent is involved. So if you factor this one out, you can see only this part showing up in there. So using this formula, we can have a little bit of estimate on this guy in here. So namely, this one is this function times this number. That's what this one is indicating. So here it is. The same formula, we are really thinking about controlling this one by dividing that m to the 3/2. So if you divide that by m to the 3/2, and this whole thing can turn into this beautiful expression called Riemann sum. With that much of a power, that becomes a Riemann sum. Once it becomes a Riemann sum, it's under control. This is approaching something. That something was that integral value. So that's the main motivation we're considering this one. The dominating term in here, it's a fast-growing term, you have to take that down by dividing everything by this one. So if you divide that, that one becomes 1/m to the 1/2. This one is still there and had this magnitude down there. As you can see, that doesn't grow too much, so eventually this approaches 0. We'll see that. And this one divided by that only varies between 0 and I think 1. So this is also approaching 0. So this you have to be a little bit careful. But these two, I think it's obvious. And that one, they're just simply approaching 0. And I wrote it down here. That main term that grows really fast, by dividing by this guy, we have constant showing up. So here we're talking about this one in here. So how can we say something about this part? Because this is not very explicit, and squeeze theorem is always the way to go. For that, we use triangle inequality. So we change to absolute value first and add them later. If you swap the operation, order of operation like that, it's triangle inequality. It becomes larger. And you further, you replace this one with the maximum possibility. That was 3. So if you replace that with a 3, and it'll give you a better estimate. Here it is. If you replace it with a 3, then this is a constant. As you can see, the sigma adding 3, 1 through m, that's definitely 3m. So m to this power is still there. So you can see it's slightly more than 1 power. So therefore, eventually it approaches 0. So that guy approaches 0, that guy approaches 0, that guy approaches 0, that approaches 0. So all you're left with this whole quantity is approaching 4/3. So that's very good for that particular form of n. We have a nice behavior. That's alpha, close to alpha, because that is not n. And this will be a good candidate for beta. We have more things to prove, as namely, what if it's just a random number, right? Is that going to change, or it's going to stay in that shape? So here I think I summarize it for you. It's everything we talked about. So if n, that is a perfect square, is rephrased like this, so this is the key part. We want to write this one in terms of n, if n is perfect square, so that's n. So what is m is n over 2, so if you put n over 2 there, you can see 3, 2 is multiplied by 2, so that's the correct power. Alright, so for n equals m squared, this seems like a right power. Alpha is 3 over 4, and beta is this 4 over 3. But that's a special case. We have to show that this alpha and that beta is the same, stays the same as n being arbitrary number, not just a perfect square, which is stated as this question, as randomly approaching infinity, not just hopping over to the perfect square. Is this behavior still valid? The answer is yes, and here's how we're going to approach. Here's one perfect square, here's a next perfect square. If n is not a perfect square, it's going to be somewhere in between, over some perfect square and the next perfect square. So we're going to see how this Sn divided by n to the 3 over 4 behaves if we know how this guy and that guy behaves. Right? See what's changing. We're going to compare this one here. M squared is less than n. Obviously, s, the top numerator, is less than, and I didn't change the denominator. So this inequality is justified, and that's the same. I mean, correct. If you look at it here, that part over there, very good. N is less than n plus 1. If you change the right bound, of course, there are more squarish number. Again, the denominator did not change. So we have this inequality for the quantity in the middle. But I guess what I'm doing next is I have to further change this one or that one down to expected shape. So I looked at this one here and use this one in there and make it even bigger. So to make this one even bigger, I replace the denominator with a small quantity. So I kept that numerator. Denominator is replaced by smaller quantity. Realize that's not what I did. I just insert this additional thing in there. So we know the behavior of this one right there. That approaches 3 over 4, and we just have to deal with this additional part. Again, this is what we have calculated, some perfect square, 2 over 3. That's, you know how this one behaves as m approaches infinity. As n approaches infinity, it forces m approaches infinity. So we just have to deal with that. That one approaches 1. So it was an equality. So this time I'm actually replacing this one with a smaller denominator. Then it makes it larger, and that justifies this one. Sorry about the unable to understand what my solution is, where my solution is going. So again, if you replace that with a smaller quantity m squared there, that changed m over 3 over 2, m to the 3 over 2. Then this is easy to see that approaches 1. Right, that approaches 3 over 4. That obviously approaches the same power, m plus 1 divided by m, that approaches 1. So we show that this one in the middle is staying below of 4 over 3. I don't think this is absolutely right, because this guy is slightly bigger than 1, and I don't know how this one really approaches 3 over 4, so I should really throw in small quantity, that epsilon, which is different from that epsilon I used before. But this epsilon definitely goes to 0 as we throw in, as we send n to infinity. So that's actually a correct inequality. This approaches 4 over 3, the right upper bound. That doesn't mean it is less than 4 over 3. It could be slightly better. But if you think about it and how this one behaves, and that you can just always replace this quantity over 4 over 3 with a slight of error term involved in there. That's less than that by definition. Whatever is different from 4 over 3 but that should approach 0 because of that behavior. Alright, sorry about the typo. Just go to next page. So we're doing the same thing with to the other directions. So it's the same inequality. Now I think they're playing with this inequality there. This is what we want to know. It is greater than that part, so we insert this 2 part so that we know where this one is going. This one is going 3/4, so we have to deal with this one. Also, we have the same conclusion that if this approaches 1, then we have the other direction squeezed down to the same number. So let's see what the next one says. So here, this part is replaced by the smaller quantity. To do that, I kept the numerator. The denominator must be larger than that, right? So here, using this larger quantity, replace that with a larger quantity, m plus 1 squared, so that's 3/2. So we have the same power right there, m divided by m plus 1 under the same power. So that again approaches 1, like before. So we have the same conclusion, that the same thing to put it there. There's some, well, I think allowing this epsilon being negative number, error term, whatever it is, that is different from that part, I think that'll do. So let me just write it that way. So correct inequality is this one, greater than or equal to 4/3, plus minus a little bit of that, but that approaches 0. So eventually that approaches that quantity. Well, this inequality alone doesn't imply anything, so we have to combine it together. Let me go to that part. And here it is, and I should say, well, this is correct. If I don't have this limit, I should throw in plus epsilon 1 and epsilon 2 and delta something else. So correctly conclude that is squeezed down to the same number 4/3. So we're concluding that alpha is a 3/4, beta is a 4/3. Well, that's it, and I hope you enjoyed my solution.